Dim openings, or black holes, might just be one of the most spellbinding and odd quirks in the universe. They are immense beasts concerning control, yet at the same time, they are for all intents and purposes intangible to us. A black hole can weigh perhaps 2 to 4 times the mass of the Sun, yet because of the assessment placed into them over the last few decades, we've transitioned from knowing practically nothing about them to uncovering increasingly more about these fascinating cosmic entities. Recently, researchers have revealed that we've finally gotten a glimpse of what lies inside a black hole. This new information illuminates nuances that the scientific community may have overlooked initially. Before diving into the details of these discoveries, we must first explore the basics of black holes. Although many of us have a general understanding of what black holes are, there are still considerable gaps in our knowledge. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept was purely theoretical, and it took nearly half a century before scientists could gather evidence to confirm their existence. This breakthrough occurred during the 1960s when astronomers were studying a gathering of stars and discovered a peculiarly bright blue star emitting X-rays. This star was not a dead object, it was orbiting a massive black hole. Upon further examination, scientists found that the X-rays were not merely moving around, they were being pulled into the black hole the star was circling. This discovery led to the term black hole, providing substantial confirmation that these cosmic phenomena truly exist and were not just a figment of Einstein's imaginative thinking. Once this was established, scientists worldwide began to investigate further. This particular black hole was named Cygnus X1, located in the constellation Cygnus, about 6,000 light-years from Earth. It was no small discovery. Cygnus X1 is about 15 times more massive than the Sun and is extremely dense, creating a strong gravitational pull. This gravitational force is so intense that not even light can escape it, giving rise to its classification as a black hole. The concept of a black hole is both captivating and terrifying. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close will be pulled in, disappearing forever. This inherent danger emphasizes the necessity of understanding everything there is to know about black holes. After the discovery of Cygnus X1, scientists began searching for other black holes and found that there may be more than 100 million black holes in the Milky Way alone. However, because they are incredibly difficult to detect, we still lack an exact number. Current estimates suggest there could be several million black holes in our galaxy, underscoring the critical importance of studying them. The fundamental characteristic of black holes is their gravity. Their gravitational power is so extreme that anything that enters gets compacted down infinitely until it transforms into a singularity. In simpler terms, black holes function like immense vacuum cleaners, sucking in everything nearby. One of the most disturbing aspects of black hole research is that if a person were to fall into one, they would undergo a process called spaghettification, where they would be stretched and torn apart by gravitational forces before reaching the singularity. So, it's safe to say that stepping into one is not advisable. Now, could we ever be in danger? The closest known black hole to Earth is about 500 light-years away, so we are not at immediate risk from them. However, the study of black holes raises intriguing questions about the universe's fate and our place within it. In 2021, researchers captured the first clear photograph of a black hole, specifically the M87 black hole. This landmark achievement involved imaging the black hole over several nights. Each image provided scientists with more evidence, and they stitched the images together to create a composite view. This process revealed that there are 3 layers to a black hole, illustrating that it is not merely a singular void of nothingness, as many people might think. To reach the nothingness at the center of a black hole, one must pass through 2 distinct layers. The first layer is known as the event horizon, which serves as the last boundary. Once you cross the event horizon, there is no turning back, you will inevitably be sucked into the black hole, and everything beyond that point is irreversible. The second layer is known as the photon sphere, where light orbits the black hole. Any light that enters this region is trapped and cannot escape the black hole's gravitational pull. Finally, we arrive at the third layer, the singularity. This is the point at which everything that enters the black hole gets compacted down infinitely, becoming a singularity, a point of infinite density. The study of black holes also raises philosophical questions about the nature of reality. For example, what happens to information that falls into a black hole? This leads to the famous information paradox, a topic of considerable debate among physicists. Some theorists propose that information is lost forever, while others argue that it could be preserved in some form, perhaps on the event horizon itself. This question touches upon fundamental principles of quantum mechanics and our understanding of the universe. Additionally, black holes can be classified into several types based on their mass. The first category is stellar black holes, which form from the gravitational collapse of massive stars after they exhaust their nuclear fuel. The second category is supermassive black holes, which reside at the centers of galaxies and can have masses equivalent to millions or even billions of solar masses. The formation of supermassive black holes is still a topic of active research, with various theories attempting to explain their origins. Another intriguing type is the intermediate black hole, which falls between stellar and supermassive black holes. These are less understood and are thought to form through the merging of smaller black holes or the direct collapse of massive gas clouds. Understanding black holes also has practical implications for our understanding of the universe. They play a crucial role in galaxy formation and evolution. The gravitational influence of supermassive black holes can affect the orbits of stars and gas in their vicinity, contributing to the structure and dynamics of galaxies. Moreover, the study of black holes has led to significant advancements in technology and methods used in astrophysics. The techniques developed for observing and imaging black holes, such as the Event Horizon Telescope, have broad applications in other fields of science and technology. In conclusion, black holes are a captivating area of study that continues to challenge our understanding of the universe. From their formation and characteristics to their implications for physics and philosophy, there is still much to learn about these enigmatic entities. As research advances and technology improves, we may uncover even more about the nature of black holes and their role in the cosmos, further illuminating the mysteries of the universe. Spacetime, where the laws of physical science as we most likely know them are independent, presents a scenario where we can't guess what happens straight away at the quark. The thickness is unlimited, and the regulations of material science, as we understand them, neglect to exist. What makes this endlessly more terrible is the fact that every single black hole you study will be absolutely novel in comparison to the last. They do, in fact, follow something fundamentally the same as a three-layer concept. However, the way they function could be incredibly unique. If this were anything else, all we'd hope to do is return quickly to those telescopes and simply focus on the fundamental worries in detail. But with black holes, you can't genuinely do that. Scientists can study black holes by inference, observing the radiation they emit and the gas and debris that surrounds them. Sending a probe, like the Voyager, into a black hole is unfeasible because whatever enters the event horizon is pulled toward the singularity, where it is compressed to an infinitely small point. So, you can't definitively spend billions of dollars just to get an impression each time. The moment the probe gets close enough, it'll just be crushed into nothingness. This presents an incredibly clear problem. Scientists are left with no choice but to focus on these phenomena in a two-dimensional way, despite their three-dimensional characteristics in reality. To make matters even more challenging, there are the issues of every single black hole being unique and the laws of material science as we understand them breaking down when we try to explore within. This means that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that researchers haven't been involved. There are plenty of theories and explanations regarding black holes, and with each one, things become increasingly interesting. One of the most compelling theories about the formation of black holes is that they are produced from collapsed stars. When a star exhausts all of its fuel, it can no longer generate enough energy to counteract the force of gravity that is continuously pulling inward. Consequently, the star begins to collapse in on itself, becoming denser as it does so. If the star is massive enough, this process can continue until it transforms into a singularity. To understand the possibility of black holes, NASA scientists turned their attention to the center of the galaxy, M87. Astronomers observed regions of extremely hot hydrogen gas that were rotating at an astonishing speed of 1.2 million miles per hour. The sheer force of this rotating disk of gas should have caused it to fly apart, however, it didn't. Scientists concluded that there must be a tremendous mass concentrated at the center of the galaxy to prevent this from happening. This immense mass weighed as much as several billion suns and was likely a black hole. But that's not the only theory about black holes. In 1963, the New Zealand mathematician Roy P. Kerr used Einstein's equations of gravity to provide the best description of a rotating black hole. Kerr showed that a rotating black hole wouldn't collapse into a point, as previously thought, but rather into a ring of fire or a thin circle. The circle would rotate so rapidly that emanating forces would prevent it from falling in. This rotating disk of matter is known as the ergosphere, and it is the region surrounding the black hole where the laws of physics begin to break down. The most interesting part of Kerr's formulation was that it implied the existence of an Einstein-Rosen bridge, commonly known as a wormhole. This is a theoretical passage through spacetime that connects two separate points in the universe or even two parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in an equivalent universe. To understand how this works, we need to consider the concept of spacetime in Einstein's theory. Space and time are not independent entities but are interconnected, forming a four-dimensional surface called spacetime. Objects with mass curve the surface, creating a gravitational field that causes other objects to move toward them. Now, imagine a piece of paper representing spacetime. If you place two weights on the paper and define a boundary between them, this illustrates how things travel through the curvature of spacetime. Spacetime yet envision a situation where you could overlay the paper into equivalent parts, moreover, make a simple course between the two centers. This is the key idea behind a wormhole. It's a simple course through spacetime that partners excessively far-off concentrations in a second. Wormholes aren't just a sci-fi thought, they are, as a matter of fact, a figure of general relativity. Though no one has ever seen one directly, the explanation is that wormholes are naturally unstable and would separate rapidly. However, the presence of an Einstein-Rosen framework would imply that dark openings are not just boundless vacuum cleaners, they could also be doorways to various areas of spacetime. So, could we ever use a wormhole to go through reality? Unfortunately, the answer is probably no. Not only could we not settle a wormhole, but it's also unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute cutoff on how speedy anything can travel through spacetime. Yet, even after this, the theory of wormholes and dark openings as pathways to various bits of the universe, or even to different times, has been a subject of interest and hypothesis among physicists for a long time. The possibility that there might be simple courses through the surface of spacetime, allowing travel across colossal ranges or even into the past, could potentially be moderated on the remote chance that we could achieve it. One of the most intriguing ideas in this area of study is the Morris-Thorne wormhole, which is named after the mathematician Kip Thorne, who first described it using Einstein's equations of gravity. This type of wormhole is fundamentally a hypothetical shortcut through spacetime that could connect two distant centers, like two novel universes or even two different times within something almost identical in our universe. The Morris-Thorne wormhole is often imagined as a ring-shaped doorway, like the mirror in the narrative of Alice in Wonderland, where walking through it could transport Alice to a reality where animals talked and logic didn't always apply. In the same way, going through the Morris ring could theoretically deliver an explorer to another universe or some other time where the laws of actual science might be generally unique from those we are familiar with. However, the prospect of wormholes for interstellar travel or time travel is not just fascinating, it's also a subject of conversation and debate among physicists. Some have raised concerns that wormholes, and particularly Morris-Thorne wormholes, might be unstable or hard to navigate due to the intense radiation and subatomic forces involved at their entrances. Scholars argue that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity and not the quantum forces that govern radiation and subatomic particles. To grasp the true nature of these phenomena, another theory is required that can unify the laws of gravity with the quantum theory of radiation throughout the universe of science. This is known as a theory of everything, a single theory that can bring together both Einstein's theory of gravity and the quantum theory. M-theory, a popular speculative theory by physicist Edward Witten, has been working towards a theory of everything. While there are many different versions of what this could be, the one that has shown promise is superstring theory. Superstring theory unites gravity with the theory of radiation. It suggests that subatomic particles are tiny vibrating strings, and that the universe is an arrangement of these strings, in much the same way as different musical notes correspond to different vibrations of a violin string. One fascinating aspect of superstring theory is that as a string moves in time, it curves the fabric of space around it, creating black holes, wormholes, and other intriguing structures predicted by Einstein's equations. This implies that superstring theory not only consolidates Einstein's theory of gravity with the quantum theory, but also encompasses many of the mysterious phenomena we observe in the universe. However, there's something about this theory that complicates its initial appeal. Superstring theory requires 10 dimensions of spacetime in which the strings can vibrate. This is very different from the 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. It is difficult for us to imagine what these extra dimensions might be like. Nonetheless, physicists have developed some theoretical models that can help us understand. Consider a 2-dimensional lake populated by fish that are only aware of the dimensions of length and width. To these fish, there is no such thing as height, and they couldn't imagine what it might be like to live in a 3-dimensional world. Yet, if rain falls on the lake and causes it to rise, the fish can observe the effects of the 3rd dimension, even if they can't truly comprehend it. Similarly, physicists believe that we may not be able to see the extra dimensions of our universe, but their effects could still influence the reality we experience.